Okay, hello. Today we are continuing with RGB technical presentations, and we have a third episode addressing more details about smart contract data, their structure, and details on RGB state data and how they are all organized all together. Last time we've gone through the data structures hierarchy, giving a large overview of what data structures are involved inside RGB. Today we will be digging into the anatomy, and next time we will go into even more details on how specific parts of this data are used to structure the commitments and maintain the overall system security. You remember, this is a slide from the last presentation. You remember that RGB as a system, it consists of independent smart contracts. Each smart contract starts with a genesis block. Well, sorry, it's not a block, clearly, we call it node, with a genesis node, which is basically a piece of data. And this node is followed by a graph, directed acyclic graph of state transitions. And today we will be examining these data structures in more details. Again, I would like to emphasize that it's very important. The contracts, they're completely independent and non-interacting with each other. They are isolated, which makes the system quite different from other systems. So we have basically with RGB smart contract, we have a genesis node and state transition nodes. These state transition nodes, they create a graph, and genesis node, actually, we haven't talked about that much yet. We will be talking much more in the fifth part of this presentation. The genesis, unlike other state transitions, it commits to a schema. And the schema is basically a structure that defines how the data inside genesis and state transitions should be structured and what validation rules should apply during the graph growth. So the schema is not a part of RGB smart contract because it can be used by multiple RGB contracts, by multiple genesis. And a typical example for a schema is the assets schema. We're actually moving right now to have a set of different schemas for different types, like stable coins or more traditional securities like shares and bonds, because they have a different use profile and they will be different in their functionality. So actually, a schema defines a class of smart contracts like assets or stable coins or identity or something else. And that's why the schema itself, its data are not part of the smart contract, but the genesis commits to the hash of the schema under rules of which this contract actually functions. Additional to this data, the nodes in RGB smart contract, as well as schema, are allowed to have scripts. We have selected simplicity script language to do the scripting, and these scripts can be present at the level of the schema. Basically, these scripts will be applied for all RGB contracts acting under some schema. An example of that I can provide, for instance, if you have any form of asset or stable coin, you basically need that the sum of inputs must match the sum of outputs. And this is part of the validation procedure. And this part is basically expressed as a part of the script, and it can be expressed in simplicity language. And it's quite obvious that the place to put the scripts is the schema itself, because this validation rules applies to all the contracts. And the schema also defines which parts of the scripting can be enhanced by a particular contract at genesis level and state transition level. Because again, if you have a validation for assets, you don't want genesis or state transitions to change the validation rule, to diverge from this rule that the sum of inputs must be equal to the sum of outputs. So with the asset schema, you prohibit scripting extensions to the asset validation. But you may have different situations where you would like to allow script extensions. That's why, in general, genesis and state transitions, they are allowed to have also their own scripting, unless it is prohibited by the schema. And also, genesis can prohibit the script extension for state transition. So it's kind of hierarchical rule applied where the scripting can be used. We will pay much more attention to schema, scripting, and validation in the fifth part of the presentation. So not the next one, but the one after the next. And I will get into much more details. So today I'm not digging into this direction at all. I'm just pointing out that the script is a natural part of genesis and state transitions, but it is not always present, and it depends on the other factors like schema. So both genesis and state transitions, we name them nodes, smart contract nodes. It's a small pieces of data. They are very similar, and at the level of RGB library, they have the same API. So both genesis and state transitions, they have the same API because basically you need to apply the same procedures to both of them. And the main difference between genesis and state transitions is that genesis created only once by an issuer, and it is the state we are starting with, all of the users of the contract starts with, while the state transitions are the evolution of this initial genesis data. So while sharing the same API, they have a small differences. Like, for instance, it is only genesis which commits to the schema and network ID of the system, because you do that once. And with the state transitions, you will have such entity as ancestors. I will be explaining what are they. And but again, to make the API more streamlined, the node, it has ancestor method always, and for genesis it returns just an empty list, which again simplifies the use of this structure. So in many places, well, first of all, if you're a wallet developer, you will never ever touch these low-level data structures. You don't need that. It will be presented with much more high-level structures. But if you will be developing for RGB internals, you will find it useful to use the node trait as a main tool to access both genesis and state transitions. And it is the way it works at the level, for instance, of validation procedures. Smart contract nodes assign both. So from now, I'm talking about the node, which means both genesis and state transition. And these nodes, they create a state assignments. So we are digging into the structure of the node, and the core part of its structure is basically how we apply state data to some transaction outputs. I was already explaining that idea of single-use seals, and that whenever we name a transaction ID and output number, it is basically a seal definition, meaning that when that output is spent, it is a special event with which we can follow with a state update. And each node, it assigns a state data to a set of seals. And the node can have multiple state assignments. So let's figure out some specifics of the terminology here. We are talking about date, states, and assignments. And what is the difference between these three things? First of all, state is any data of some well-defined type. And the type of this data is named data type. So state always have some specific data type. Of course, you can use the same data type, like an integer, for instance, 32-bit integer, for different type of states. So there is a strong difference that state always has a single data type, but different state data may have the same data type between them. That's very intuitive because if you program, you can have multiple variables. You can think of state as a variable, and you can have multiple variables of the same type, data type. But of course, each variable have only a single data type. So the same relations applies to the state and data types within the nodes. The assignment is a state, the actual state data, linked with a particular sealed definition. So basically, we assign state to some transaction output. That's why we call it state assignment or just simply an assignment. And actually, I was talking about state type. That is not strictly correct. The correct name is assignment type. So, for instance, I will be explaining a little bit later. You remember probably from the first presentation, I was talking about that RGB is a digital rights management system. And we are frequently talking about digital right. Each form of a digital right is basically an assignment type. For instance, with the assets, we will have an ownership right, the owners of the asset. And each time you assign some amount of asset to a particular owner, you do a state assignment of type asset ownership. So asset ownership, it is assignment type, and you can have a multiple state assignments under this type. Another example of assignment type is a right to do a secondary issuance. So I probably need to move to the other side. So yeah, here is an example. So with a secondary issuance right, you assign the right to extend, to inflate the issuance to some specific transaction output. And it's a different assignment type. And the point is that within the node, you may have multiple assignments under multiple types. So you have a hierarchy of two levels. First of all, you have different assignment types of different digital rights, like asset ownership or inflation or some other types. And under the assignment type, you can have multiple state assignments. And each state assignment consists of state data and sealed definition. So that's the structure of it. I covered this slide. I covered this slide and this one. Yeah, correct. It is important to remember that state of different type are always isolated from each other during the validation process, both at the simplicity script level and schema level. And you wouldn't be able, for instance, why we need that? When you accept the assets and validate them, you shouldn't be able to break the fungibility by taking into account who is the issuer. If the issuer operated within the rules defined by schema and genesis, you have to accept that. So that's why we would like to differentiate very well the validation of different digital rights from each other. And when I will be talking about the validation, I will be showing that basically you still validate the structuring of the digital rights using a schema. For instance, you still validate that there might be only a single assignment of a secondary issuance type and multiple assignments of an ownership. And you do that validation with a schema. But when you validate the state data within assignment type, you will never see other types of state from inside the validation script. And again, I would like to point out that the assignment type is not the same as the data format. So the data format or the data type is basically a type of the data. And I will be covering briefly what data types could be. But for instance, it's a string or integer, while the assignment type it's a type of the digital right. It's more semantic thing. So it's assignment type is a ownership or secondary issuance or identity and so on and so forth. And the fact is that additionally to the state, I will probably start with this one, additionally to the state and all the state assignments, each node may contain a metadata records. And unlike state assignments, they have no isolation at both schema level and simplicity script levels. And actually, you can use the metadata to share some information between validation procedures operating on different state or on different assignment types. I will be digging into how to structure the difference between state data and metadata in a moment. But before that, yeah, probably I will start with this one. I think the order of slides is not perfect, so I will change it after the presentation. So what is the difference between state data and metadata? Unlike metadata, state can evolve, so it changes over the time. While metadata, they're defined once and forever. For instance, at the level of genesis, you use metadata to give a name to the asset or a ticker to the asset. And this ticker and name will apply to this contract forever. No matter how many state transitions have happened, you still use the same name. While with a state, you always use the state of the last state transition. And if validation rules and simplicity script and schema defines that you also have to use a previous state, you can use it again, but it's not obligatory. While with metadata, you usually start with the metadata defined at the level of genesis. Also, the second very important difference is that state data, they are always assigned to a transaction output. And the fact that this transaction output is spent means that this data, this state data, are not final. And there is a state transition after that. And to validate them, you need to check that last state transition. So this is how you can make a provable history, and you will be always sure, do you have an end version of the state data or some of the previous version of the state data? Because we are not assigning metadata to transaction outputs, there is no such mechanism for metadata. That's why I said that the metadata, they don't have a validity frame. So if you define metadata in genesis, you can't define a point after which it wouldn't be valid anymore, because you don't bind them to the Bitcoin transactions in no way. State data are validated in isolated mode, while metadata, they are validated in general, and they are provided to the validation script for each procedure that validates state data. So the procedure that validates state data, it sees the state data and metadata always. So in this way, metadata may be used to have some shared and common information for validation procedures for different assignment types. State data can contain homomorphical encrypted data. I will be addressing that and explaining this part a bit later. And state data and metadata, they are different in a way you do the conceal operation. You remember that with RGB, we're paying strong attention to privacy. And each piece of the data, each state transition, they have a special conceal operation that converts explicit data in an under human readable or computer readable format into noise data, concealed form of the data, confidential data. So for instance, with amounts, if you have amount of some asset, the explicit format is actually like 5 or 10, how many assets do you have, while the concealed format, confidential format, is a Pedersen commitment. And this Pedersen commitment, from this Pedersen commitment, you can't guess how many assets is there, but you still can apply arithmetics to this data and make sure that the sum of inputs equal to the sum of outputs. So this type of conceal procedure is called homomorphic encryption. And homomorphically encrypted can be only state data. Additional to homomorphic encryption, there are two other types of and forms of data concealment. They are just a simple hash and Merkleization of the data within the Merkle tree that allows you to reveal some of the data without revealing the rest of the data. So all the metadata and assignments within the state transitions, they are Merkleized. So you are not required to reveal all of them always, and this procedure applies to both metadata and state data. And the end data within the metadata can be hashed, while within state data you can use either homomorphical or hashable way of concealment. I will be talking about concealment and confidentiality of RGB in a separate talk. Probably it will be part of the schema and validation, or maybe it would be a separate presentation because there is a lot of information and it requires quite a lot of effort to explain how it all works. State data, so this is all about the difference between state data and metadata. But additionally to the difference, there are some common parts of them. They share the same data types for non-homomorphic data. So whenever you define within the code data type, you will know that you can use this data type for both storing the metadata or for storing the state. With a schema, you use the same rules of occurrences. I will be explaining what occurrences are during the schema talk, but basically each state transition it may contain metadata records of some type, but you can define and restrict with the definition of secondary issuance right within Genesis. And this is a restriction on the number of occurrences of this particular state type within the state transition. And you use the same mechanics to restrict this number of occurrences both for state data and metadata. And I already said that they use the same procedure to store the metadata and state data, same Merkleization procedure to store commitments to them within the state transition node. A bit more about these data types that can be used by state and metadata. State, as I said, it has three data types, classes of data types actually. Homomorphically encrypted data. It is 60-bit values which are encrypted using Pedersen commitments. We name them through the code as amounts in most of the case because you use them to represent amount of some asset. And void data. Void data type for the state is actually that there is some digital right which don't need any additional information about it. Again, as I already was mentioning, a secondary issuance right. There is no data that you can actually attach to the right. So you can have a right to do a secondary issuance wherever you spend this transaction output. And it means that this state assignment, it has void data. So there is no data attached. And of course, void data, they are not encrypted because they are basically empty. And hashable data, so all other data types like signed and signed and unsigned integers, float numbers, strings, byte strings, or blobs, or even specific types like public keys, signatures, they have their own data type definitions within the code. And for the confidentiality, they are just hashed. So if you receiving some history with the consignment, most of the data there will be hidden because you will have just a hash representation of those data. You wouldn't be able to guess what are those data. And as I said, these classes with the state, you can use all three classes: homomorphically encrypted, hashable, and void. With the metadata, you use only hashable data types. So, as example that I gave already with assets, for an asset ownership right, you use homomorphically encrypted data, and for secondary issuance right, you don't use the data, meaning that you use a void data. The last part of the RGB node, smart contract node anatomy is the script, an optional script extension. And I already talked about that briefly, and we will have a separate talk dedicated to schema and scripts, where I will be addressing that in more details. To give a very high-level differentiation between the contract node and schema, here I present the structure for both of them. So the contract node it defines state data, metadata, and simplicity script. State data, they are hierarchy of state assignments organized by type, and each state assignment has a seal definition and state data assigned to that seal. Metadata is basically a set of metadata records of different types, and simplicity script can be present or not. While the schema actually defines what assignment types are possible and what restrictions are applied to them. It also defines what metadata types are there and links each data type to the metadata type. So for instance, you can have a data type is a string, and when you define an asset, you have a name, ticker, and description, and they all are strings. And actually, schema is the thing that says that you can define metadata of type name, ticker, and description, and the data type for those metadata is the string. Additionally to that, it defines types of state transitions. So you can combine state assignments and metadata in different ways within the state transition. And schema defines these ways as types of state transitions, and each RGB contract can contain state transitions of multiple types, and schema also defines how these different basically how to construct a graph of stations and how to organize state data and metadata within those state transitions. So that's why it's quite a complex topic, and we will need to spend more time on that in one talk from now. Last time, I was showing this slide, and we were explaining how we move from one state transition to another with all these assignment, seals, anchors, and so forth. And right now, I would like to dig into more details and explain more particularities about that, especially because I got quite a lot of questions regarding how these anchors and state transitions and assignments interoperate. So if we usually draw a Bitcoin transaction as a box, one side of which has inputs and the other is outputs, how we can draw a smart contract node? Well, as I said, it can have a set of metadata, it can have a set of state assignments, and new state assigned to new outputs, and these state assignments can be of different type. Additionally to that, it has an ancestors. So previous state assignments which are basically invalidated by this state transition. For sure, for Genesis, the list of ancestors is empty. For all other state transitions, it is non-empty. And a section for scripts. I would like to pay special attention that there is no version in RGB nodes. And why we don't have a versioning, it is basically with RGB, the version, even if we will have some upgrades, the version can be changed within the smart contract. So it is basically defined at the level of schema by the issuer. And once the issuer issues a smart contract under a particular RGB version, system version, this version will always apply to all the data within that smart contract. If we will have a second version of RGB and there will be a need to upgrade, it basically issuer who is required to do the new genesis and create new smart contract and migrate the assets or whatever data he issued. By doing that, we avoid the risk of hard forks, soft forks, and many other problems. So basically, with the client-side validation, we can't do the versioning within the RGB particular RGB contract. Now, when we gone through the anatomy of the smart contract node, I would like to go through this process once again, but from a different perspective, addressing those questions that I received today, and pinpoint how different parts of the state transition are related to Bitcoin transactions and anchors. So we will start with some state transition. We name it current or the original state transition. And internally, it contains a set of assignment types. And within each set of assignment types, you have a set of state assignments. So this containment is shown by one to many. So each state transition may have a multiple assignment types, and each assignment type can have a multiple state assignments. And state assignment basically within itself, as I said, it contains of state and seal definition. So define fields. And field is transaction output, meaning transaction identifier and number of the transaction output within that transaction. And it is important to see here that while each state assignment is linked to a single transaction output, we have multiple to the same transaction output. First dependency here, multiple state assignments can define the same transaction output as a seal within that assignment. And here we move from the state transition structure into a transaction structure. So the transaction that contains output, which is used as a state assignment by one of the state transitions, is named an assigned transaction. Because we have a second type of transaction, which is named a witness transaction. And this is the transaction that spans the transaction output that contains some state, that has some state assigned. And of course, the transaction, Bitcoin transaction, it may contain multiple inputs. And each of the inputs, it points to some transaction output, as you know. So witness transaction can point to multiple transactions output with a multiple states. So witness basically can aggregate and can be related to many, many state assignments from even different state transitions and even from different RGB contracts. And this happens at the level of witness transaction. How we will differentiate with all these three levels of nested relations? Well, witness transaction consists, of course, of transaction outputs. And this is the place, transaction outputs, where we will be putting our commitments to the new state. And we use a special procedure called LNPBP3. It is a standard. How we define which of the outputs within witness transaction must contain a commitment. Briefly, we use an RGB contract identifier, which is a hash. We divide it on the number of transaction outputs, which is a constant, and we know into which transaction output we need to put a commitment. And this means that if we have a witness transaction related to multiple RGB contracts, we may differentiate these commitments to these contracts into a different transaction outputs. So we prevent a situation from happening where two different independent contracts have to be committed from a single transaction output. However, it could be not always the case. First of all, we may have a single output only, or since there could be thousands and thousands of RGB contracts and transactions usually contain 2-3 outputs, it would be quite frequent where the same commitment has to go in the same transaction, witness transaction output. And this is where the anchors come handy. So witness transaction output commits not to the new state transition, but to this intermediary structure we name anchor. And there is a one-to-one relation between anchor and transaction output. So there is always a single anchor per transaction output. But each anchor can commit to multiple new state transitions under different RGB contracts. And by doing that, we actually can handle the situations where independent RGB contracts assigned to the same transaction output, or where independent RGB contracts, the outputs assigned by independent RGB contracts are spanned by the same witness transaction that has just a single output, where we need to commit to the new state under different smart contracts. And that's where we use an anchor, and the anchor, it embeds a multiple commitments to state transition inside a single data structure. The last part of this story is basically that a new state transition also commits to the ancestors, which are basically a previous state assignments invalidated by this state transition. I understand that it's really probably hard to understand, to grasp all this multidimensionality from a talk. So we will be releasing the slides, and I will be happy to hear the questions. This slide actually represents the same thing like this slide from the previous presentation, but in a different form. And I hope that it will address the most of the questions I got from the previous presentation regarding interaction of these data structures. So we have just very few slides left. I will try again to explain the same concept, but again from a different perspective. So here we have two RGB contracts with their histories, and the last state transitions under one and the second, first and the second smart contract, it assigns some state to different transactions. And there is some witness transaction that spans those outputs, and all the structure that we just discussed, how it applies to the situation. Here, basically, we divide the ID of the smart contract, and we find out into which transaction output we need to put a commitment to a new state transition. And if they are different, we are quite happy. But if they are not, so we need to put the commitment into the same transaction output, we use this anchor, which is basically consists of slots internally. And these slots are slots used for the commitments. And we use the same mechanic as I just described. We divide the ID of the contract on the number of those slots. And we are able to define into which slot the commitment should go into. And basically, we put the commitment to the new state transition into that slot, and that state transition will point to its ancestor state assignment. So again, we have the same structure like we have on this slide, but for two different RGB smart contracts. To summarize the interaction between transitions, transactions, and anchors, Bitcoin transactions. There are two types of Bitcoin transactions from RGB perspective: assignment transaction and witness transaction. Assignment transaction are basically a transaction that contains outpoints to which we assign some state. And witness transactions are transactions spanning those outpoints. So in other words, assignment transaction, the transaction that contains seal definition, and the witness transaction is the transaction that closes those seals. And it's quite important to know that, first of all, if you don't have access to RGB data, you're just seeing on-chain transactions or just Bitcoin transactions from wherever they come, you will be never able to guess, is it assignment transaction or witness transaction, because all this data, they're not obvious. They're basically, if you create a seal definition, there is nothing in transaction that changes. It's just external agreement to the transaction. You just use the ID of that transaction and output number, but transaction contain no data about the seal definition. And for witness, you put a commitment to the witness transaction, but you put commitment into a public key by tweaking it. So this public key looks like any other public key, and you wouldn't be ever able to guess that this is actually key containing some commitment until you have the data from RGB. And another important thing, that the same transaction at the same time can be both witness and assignment transaction. So it is roles that apply to transaction, and both roles can apply to the same transaction and even same transaction output. So you can use, for instance, an output that contains a commitment to a new state transition, and at the same time, the same state transition will assign some state to this transaction output. There is nothing preventing from doing that. So that's about Bitcoin transactions. What about state transitions? Well, state transitions, they had this hierarchy of assignment types and multiple state assignments inside each type. And these state assignments, they point to, first of all, the state transition, it points to many ancestors per each assignment type. And from other side, it assigns multiple states of multiple types to multiple transaction outputs. And these transaction outputs are basically defined by assignment transactions. And the last data structure is anchor, which links transactions with the transitions. So basically, it provides this link between witness transaction and state transition. There may be many multiple anchors per witness transaction, but it is always a single anchor per witness transaction output. So each witness transaction output can commit to a single anchor only, but because transaction can have multiple transaction outputs, there might be multiple anchors associated with a single witness transaction. And each anchor may link to many state transitions. We have these two levels of many to many. One witness transaction can link to within RGB contract, within RGB smart contract, you may have only a single state transition within each anchor. So you can't put two state transitions under the same smart contract. And it means that all the changes that are committed with a witness transaction, they have to be made with a single state transition. Otherwise, you wouldn't be able just to put the commitment. And it is not a problem. It even simplifies this quite complex system, meaning that you always have a single state transition at the end of the day per RGB contract per transaction. The next time, so this is the final slide. The next time I will be giving more details about these commitments and anchors, how these commitments are happening, because we have a hierarchy on commitments, how the anchoring thing is working, more details about single-use seals, how single-use seals are related to anchors, witness transactions. So it will be a second part of the data structure. And today part, it was related to the data and state and the smart contract, while the next part, the next week, it will be related to the commitments to those data. And the difference between these two parts is that state data and metadata and state transitions, they present data that makes sense. Like you define an asset, their qualities, their amounts, and you operate with them. While the commitment parts, it's basically a hashed data. It's always hashed data, it's always commitments, and they are used only to validate the uniqueness of the history, and they don't contain useful information in terms of the RGB smart contract. And usually they mix they can mix many RGB contracts like with anchors, but still without any risk of the information exposure, because again, you use hashes and you are not able to guess. You wouldn't be able to guess what the actual data are behind those hashes. That's all for today, and I think we can get to Q&A session.
Perfect. Thank you very much, Maxim. It was a very good presentation. Guys, feel free to ask questions. If you need to, if we need to jump to some other slide, also let us know.
I had a quick question about, I guess, versioning. So I guess the assumption within RGB, since there is no versioning, is that in the case that any change needs to be made to a particular schema, that and since the issuer is assumed to be trusted, that any upgrade from a particular version of an RGB asset to another one, would just be coordinated by the issuer, I suppose.
Yeah, correct. That is correct.
Got it. Cool.
Because otherwise, we will run into this governance problem, and whole RGB is structured about the idea that the owner is the one who governs. And even if we will have any kind of voting that the majority of owners decide to migrate, it still will be a dictatorship of majority. So the only way we can orchestrate the migration is basically by the original creator of Genesis. And the only way he can do that is basically create a new Genesis and new Issuance, and all those who want to migrate, they will voluntarily migrate. And those who won't, sorry, they have the right not to do that.
Yeah, that makes sense. I guess the only situation where that might, the only situation I guess where that would become a concern is say a particular issuer, sets a fixed supply, and then, later I don't know why. I guess there'd be a fixed supply, and then they want to increase that, which might create a weird situation where. But I suppose if they put that fixed supply in the first place and everyone has agreed to that in the first place, then it's assumed that that will be the supply for the the duration of that asset, and if anything needs to change, then people need to opt into that anyway. So yeah, that makes sense.
Yeah, correct. You have, if you would like to have inflatable supply, you just need to use the different schema from the very beginning. But if you commit to some rules as an issuer, and everybody else know that you accepted those rules, and now you would like to change them, well, you shouldn't be allowed to do that within the same system. You can create another asset and say, okay, I was wrong. Now I create another asset which inherits this asset, and all those who are willing to exchange the previous to the new one, you can use this procedure, but you can't force everybody to upgrade, because you're basically changing the rules.
Yeah, it basically needs to all be opt-in. That makes sense.
Any other questions?
Yeah, hi. Just a quick question. That is, if we try to match this up with the structures of stash that you have mentioned in the last call, so I guess anchors will be the one that will be inside the stash database, or there will be something else that we also need to keep in stash?
Basically, in stash, you keep all the RGB data structures: schema, genesis, state transitions, and anchors.
Okay, so in that case, it's a whole bulk of data, and it's something everything that we might need in order to validate any kind of state transition will be available and should be available in the stash.
No, because validation procedure doesn't apply to stash. It applies to a consignment, which is a form of stash containing only those data that are required to a particular validation. So within the consignment, when I will be describing the validation, the plan is that I will explain the anchor part of the story and commitments part of the story, and will explain the schema, and after that I will be able to move to the stash, consignment, and validation, how they are structured. But briefly, the consignment is basically, again, it contains a schema, a single genesis, state transitions, multiple anchors, and it clearly defines an end state. And you can do a validation procedure for this end state, having only the data within the consignment. And once you validate a consignment, after that you merge it with the stash. And whenever you need to transfer one of the stashes, you extract the consignment from the stash, you conceal all the data that are not required to the new owner and to the validation procedure, and you send this consignment over to the next owner.
Okay, thanks. That makes sense.
Yeah. Any other questions? And of course, if you need to do anything complex, starting even from the Lightning Network or up to potential future DLCs, atomic swaps, anything, taproot, you do that at the level of the transaction output. So here, in the transaction output within the assignment transaction. So whenever you assign something to output, the rules of this output defines the ownership in the future history. So if you assign something to output of Lightning channel funding transaction, you basically put an asset into the channel. If you assign something to atomic swap contract in the transaction output, you put this asset into atomic swap. If you assign an output to a DLC transaction to one of its outputs, you put the RGB asset or that right, because you can do it even not only for assets, you can do that for issuance right, for instance, secondary issuance right, or identity or whatever, and you put that into the scope of this particular DLC contract. So you can trade the rights, not only tokens, but also the rights. And there are no specific mechanics to support DLC or atomic swaps at the level of RGB, because basically all those mechanics, they're implemented at the level of Bitcoin transactions, and RGB just follows. The only thing you need to make sure is that the transaction that spends that output will contain a commitment. So you still need to integrate into Lightning node or whatever node supports DLCs or atomic swaps to do that tweaking, and at the same time create a new state transition and keep it separately for the future owners. Any more questions?
I have a quick question. Is there any documentation available so we can start playing around with this? Like, you know, showing us how to use the RGB node and interact with Lightning and all these other things to kind of just wrap our head around it?
We had a demo of RGB node. We have a video recording of that. So you can check that. The Lightning network part, we don't have a demo yet. It's still a work in the progress. And if you're talking more about internals of RGB node code base, how to understand different parts of it, I think, well, we will have to finish, first of all, with all these RGB details with this series of presentations. And after that, we will be able to move to that, because it would be hard to understand without explaining what parts of RGB are out there.
Damian, have you checked our repository, which is called RGB node?
Yeah, I actually have them. I got it installed and everything. And I do the help. I'll do the command line, for help and things like that. But I guess I need a little bit more guidance. What to do?
Well,
I looked into the Rust wallet because I know
mhm.
the RGB node is built on Rust. So I said, well, let me look at the Rust wallet. Let me see what can be done with the two. But I'm just kind of like hanging out there in limbo somewhere in between the Rust wallet and the RGB node.
Well, you can't use RGB node without proper integration with existing wallet, because that's the whole point. The wallet is not part of RGB node, and different wallet developers do the wallets in a different way. So we have few groups of people working on doing their wallets or integrating with their wallets, but right now there is no ready-to-go solution. So if you will try to do it yourself, you basically either need to mimic a lot of wallet things like signatures, private keys by yourself, which can be done, of course, and but it's more quite a complex and heavy-duty stuff, or wait for one of initial wallet releases, which hopefully will happen within the scope of months or two.
Thank you.
And of course, you're always welcome to ask the questions in the chat if it's not clear how to do something with RGB node from command line. Any more questions?
So guys, if there are no questions, I think you can wrap this up.
Yeah.
Okay, so you always have me and Maxim online, so just drop us messages, join our IRC channel, follow Reddit, YouTube, and just stay tuned. Thanks, Steph. So thanks everyone for being here. And
Thank you for joining us.
See you next week.
Yeah, bye-bye.
Bye, guys.
Hey, thanks. Amazing session. Thanks.